Good evening. I'm so excited to share the topic of our research, specifically focusing on a biomimetic robotic system with Tensegrity-Based compliant mechanism. Our research problem was that we have observed several challenges associated with robot structures within current robotic operations. Essentially, while traditional rigid robots have been widely used in fabrication industries with their ability to handle massive and repetitive workloads, they can hardly operate in confined spaces. On the other hand, even though soft robots demonstrate a noticeable performance in ill-defined environments, they can neither perform load-bearing tasks nor be easily manipulated. In fact, the lack of a robotic system with adaptability and control efficiency was what our research aimed to address. Taking inspiration from biology, specifically the physiology of vertebrates, we set out to explore how robots could adjust their structural stiffness based on environmental conditions or task requirements. Studies have highlighted that the integration of bones, muscles, and joints in vertebrates ensures an efficient trade-off between rigidity and flexibility, which shares a significant similarity with tensegrity structures. Therefore, we took this tensegrity-based concept as the foundation of the research. We started with the prismatic tensegrity unit, which was comprised of two triangular plates on both sides, a hexagonal plate in the middle, and a tensile network arranged in a circumferential pattern. Based on simulations, we found its ability to be actuated and stretched when subjected to pulling forces along the primary axis. And by augmentations in a linear order, the spine-like topology was constructed, enhancing its deformability. In terms of structural performance, this tensegrity-based form provides high compliance, flexibility, control efficiency, and effective force distribution with a self-balancing mechanism. To achieve these capabilities in real-world situations, we developed a rigid flex coupling joint that allows tension and compression components to synergize effectively. Basically, we utilized its structural behavior as an actuation, which could be considered as a compliant mechanism. Once applied with external forces, this tensegrity-based structure was able to undergo stress distribution and thus transitioning to a new self-equilibrium state. Much like how muscles and bones synergize to switch configurations observed in biological systems. This control strategy ensures the robot to achieve various movements with only 3 external cables in this case. It doesn't require complex mechanical setups at each joint, which is a relatively efficient method compared to traditional robots. And we also built up a holistic mechatronic system to precisely control the movement of the robot structure. We used inverse kinematics to convert physics simulations into control parameters, and sent these data to mechanical setups through a microcontroller unit to achieve robotic movements. The entire system allows us to synchronize the computational and physical model with control efficiency and accuracy. Basically, each control parameter set of external tensile actuators corresponds to a specific configuration. A collection of parameters could eventually be converted into a continuous movement, which was the way we manipulate the robot structure in both computational and physical environments. The following framework was how we planned to validate its performance and to optimize its control system. We extracted a few sets of control parameters from simulations, and then transferred to the mechatronic implementation. As the robot navigated its environment, the sensors could collect spatial data, which was relayed back to the software for real-time monitoring of the robot's actual position. Moreover, we had repeated this process and trained the robot with machine learning approach to seek an optimal control. This methodology not only allowed us to validate its versatility, but also helped us figure out the cause of deviations from desired configurations. The experimental results showcase the robot's proficiency in both multidirectional and unidirectional movements. Most importantly, the combination of different motions enabled the robot to perform more complex movements, such as rotation combined with torsion, bending plus buckling, contraction with bending. Our findings also demonstrated that by adjusting the control parameters within an appropriate domain, we could manipulate its stiffness and range of motions. This dexterity in switching dynamics provides more control efficiency and environmental adaptability, leveraging the advantages of both rigid and soft robots. The potential of this structure accentuated as we trained its control system. We utilized the supervised learning approach so that the robot could gradually achieve biomimetic movements with an efficient control strategy. This integrated enhancement also provided robots safety and adaptability when navigating through unstructured or unfamiliar spaces. With each training iteration, the robot progressively acquired the capability for biomimetic locomotion. It can conform to obstacles or environmental changes simply by adjusting its stiffness. And what's more exciting is that these movements could be achieved with less mechanical complexity comparing to existing robotic techniques. And we believe that this kinematic advantage could benefit robotic operations in confined spaces, with potential applications extended to digital fabrication and structural engineering as well, such as biomimetic 3D printing technology or biomimicry building enclosures. Additionally, we found a few limitations. Intrinsic material properties, such as time-dependent pre-stress loss of cables and friction between components, might cause deviations, which require careful consideration for further applications. In summary, our research introduced a biomimetic solution that provides versatile movements, adaptability, and more efficient control in order to explore robotic operations in unstructured spaces. And that's it. Thanks for listening. If there's any question or concept needed to be clarified, please feel free to ask. I'm willing to discuss further. Thanks.